Hello, this is the first course in the Mathematics Applications and Interpretation standard level and high level using the Oxford IB Diploma Program textbook. This particular video is on section 1.1 and 1.2 for SL. HL has no corresponding section in their textbook because they start at what an SL would be 1.3. However, this is a good review for them as well, and therefore recommend everyone to watch this video. So today we are starting 1.1 and 1.2 on 1.1 is measurements and estimates, and 1.2 is on recording measurements, significant digits, and rounding. In mathematics and in science, we quite often deal with idealizations. I teach physics, and we talk about the frictionless plane, the massless rope. We don't worry about the moon's gravity and gravitational problems involving the sun and the earth. We don't worry about the curvature of the earth. These are all complications that you add on later as your mathematical skills develop and your scientific skills develop. How does that correspond to math? Well, in mathematics, quite often, you will be given a square, and you're told that the sides of the square all are 10 centimeters. And we never really worry about how we know that it's 10 centimeters. We just go with it. And we don't worry about the origins of the determination that it's 10 centimeters. We just assume it's 10. And when we say 10, we mean 10.0000 forever, because it's exactly 10. But in real life, we ask questions like, how do we know that it's 10? And what's the answer? Well, we measured it. Well, no matter what measuring device you use, whether it's a ruler or some kind of laser, accurate, precise device, there is always going to be a limit to how accurate and precise your measurements are. As such, every measurement is an approximation. Nothing is exactly 10 centimeters. Nothing is exactly 5 kilograms or takes exactly 30 seconds to occur. Every measurement has uncertainty. That in and of itself is not a big deal. You round, okay, so it's approximately 10, no big deal. Well, when you start building up more complicated formulas that rely upon your measurements, for example, okay, if the side has length 10 approximately, and this side has length 10 approximately, well, when I multiply them to get the area, because the area of a square is side times side, how accurate is 100, 10 times 10, how accurate is that as the result, as the value of the area of the square if the tens themselves were only somewhat accurate themselves? How do we take our measurements and extend them to more complicated measurements that are based upon the initial measurements? And to do that, we have to build up some rules of how to combine measurements together so that we don't lose the accuracy that we want, but at the same time, we don't assume additional accuracy that we don't actually have. So 1.1 is a very qualitative section. There's no math in it. It's about the concepts of measurements and estimates. And we have a couple of principles that we would like to throw in and write down. And these principles are as follows. Number one, principle number one, measurements help us compare objects and understand how they relate to each other. help us compare objects and help us understand how they relate to each other. So, back in the day, before science got very quantitative, someone would drop objects and say, oh, okay, they both fall down. Great, gravity, wonderful. But then things got more quantitative and we started to ask, well, how quickly does this object accelerate versus this object? We want to be able to compare them. If I say, oh, this object, pretty heavy, this object, somewhat heavy, well, which one is heavier? Well, we have to measure both of them and then decide based upon our measurements, which one is more massive, which one has the greater pull of gravity and therefore is heavier. So measurements allow us to compare objects and then relate them to each other. Measurements at its core, or measuring, requires approximating. Every measurement is at its core an approximation. Measurements require approximation. If a smaller measuring unit is chosen, then a more accurate measurement can be obtained. Accurate measurement can be obtained. And this seems very reasonable. If I have a measuring device like a scale that measures every gram, and I put something on it and it says, oh, this weighs 73 grams. But then I buy a better scale, a newer scale that can measure to the 0.1 grams. And it says, well, it's not 73 grams, it's actually 72.8 grams. Because the unit is smaller, the 0.1 grams is smaller than the 1 gram, we get a more accurate measurement, 72.8 grams versus 73 grams. Number 3, when you measure, you first select a property of the object that you will measure. What is it that we are after? Do we want its length? Do we want its mass? Do we want its volume? Do we want its color? So when you've measured, you first select a property of the object that you will measure. By the way, color seems a little weird because color is not really quantitative like the others. There's no numbers involved in color, but in physics, we know that color corresponds to frequency, so it becomes quantitative as well. But we'll keep it simple here. Length, height, time, mass, very number-oriented measurements. So when you measure, you first select a property of the object that you will measure. Then you choose an appropriate unit. Unit of measurement for that property. So if I'm measuring the distance from the tip of this pen to the end of this pen, a length, we're not going to measure it in miles. It does not seem like to be an appropriate unit. I might use inches, I might use centimeters. But if I'm measuring the distance from the Earth to the sun, then inches and centimeters is no longer an appropriate unit. Miles might not even be the greatest unit, although we do know that it's about 93 million miles. We might use a larger unit of measurement, something more appropriate for what we're trying to measure. So we first pick the property. We then choose an appropriate unit to use. And finally, you determine the number of units. And finally, you determine the number of units. So in this case, right, I take out my ruler and I say, oh, this is about, 5, 6 inches, whatever it is. And in the case of the Earth to the Sun, oh, it's about 93 million miles. Is it exactly 93 million miles? Well, forget about the fact that the Sun actually orbits in an ellipse, not a circle. So its distance from the Sun to the Earth is not constant. But even ignoring that, it's not exactly 93 million miles. That's only an approximation. So we will get into approximations and significant figures, which are what we use to help us approximate in the next section. So again, you pick the property, 2, you pick the units that you want to use, and then finally, you do your actual measurement. You get your numerical value. So, estimation. What is estimation? Is finding an approximation as close as possible to the value of a measurement by sensible guessing. By sensible guessing. When I look at this pen, I say, oh yeah, it's about 3 miles long, right? That's an estimate. 3 miles. It's not a really good estimate. And in fact, it's probably the worst estimate ever made in anything in the history of time, but it is an estimate. However, it's not a really good one. What we want to do is we want to come up with an approximation by sensible guessing. So I might say, well, this is about an inch. So 1, 2, 3, 4. This is about 5 inches based upon my initial sensible guess. That's what estimation is. Okay, if I use a ruler, I am estimating based upon what the ruler tells me. The ruler does not say exactly 6 inches. It'll say, or 6 centimeters. It'll say, oh, it's 6 points. Oh, what is that? Well, let me guess. Let me do a sensible guess based upon what seems reasonable from a logical mind. So estimation is finding an approximation as close as possible to the value of the measurement by sensible guessing, as close as possible. If you have a choice between a good estimate and a bad estimate, closer versus further, always take the better one. Often, still in the same little bullet, often the estimate is used to check whether a calculation makes sense. Whether a calculation makes sense, or to avoid complicated calculations. I'm not sure if you've ever experienced this, but sometimes I'll solve a problem and I'll get an answer and I'll just say, well, that answer doesn't make sense. That can't be right. Because I'll have an idea of what the answer should be based upon, well, okay, this is about 10, this is about 10, so the product should be about 100. So if I get, 2 numbers that don't give me something in the vicinity of 100, I'll know something is wrong without actually worrying about, oh, this is exactly 7.2 versus 9.6. Well, 7.2 and 9.6. 7.2 is around 7. 9.6 is around 10. You multiply them, you get about 70. Nah, that can't be right. I'm looking for something around 100. So you can estimate without worrying about the finer precision to just to check whether the calculation makes sense and to avoid needing a calculator or something that might even be significantly more complicated. And then finally, the last one for the section, estimation is often done. Estimation is often done by comparing the attributes that is measured to another one. Or by sampling. Now, sampling, that is a statistical idea, and we will have lots more to say about that later because A&I is very statistics approached versus A&A, which is more calculus approached. So we're going to talk about sampling later. But just very quickly, if I believe that a coin is fair, for example, I have a coin. I think this is a fair coin. Let's use it to pick teams, or for the Super Bowl. Let's flip the coin and heads or tails, and whoever wins, you'll kick off first, or receive, whatever you decide. So what I can do is I can flip that coin 1,000 times to kind of check whether or not it's fair. Well, if I get 72 heads out of that 1,000 flips, when I'm expecting something in the vicinity of 500, if it really was fair, I might really start to question whether or not the coin was fair in the first place. Sampling. Sampling can often tell us whether or not we get a result near what we expect. And if we do not get a result near what we expect, then we might throw away our assumption of fairness in this case. This leads to what is called hypothesis testing, which we'll get to far down the line. Or I can just say, okay, I estimated this person and he weighs 723 pounds. But then you say, wait a second, that person next to him or her, I know that person's weight, and that doesn't really make sense because that person only weighs 175 and they look kind of similar. So quite often you can use estimation to determine whether or not a value makes sense. Or you might say, well, that person weighs 175, this person looks to be the same, so let's estimate their weight to be 175 pounds. So we don't actually do any calculations. We just estimate. We make a sensible guess based upon the information that we have in front of us. So this is section 1.1. Section 1.1, very qualitative, talks about measuring and estimation. And at its core is the fact that a measurement is an estimation. So now we go to section 1.2. So this was all section 1.1. I should probably have labeled that. So let's throw it in now. I can take this and lower it down a little bit. So we have in black 1.1 measurements and estimates. Measurements and estimates. And that's not straight. So we'll try one more time. Measurements and estimates. Okay, measurements and estimates. So now we go to section 1.2. This is still not yet in the HL curriculum, but it's a good preface to the HL curriculum. And for 1.2, we have recording measurements, significant digits, and rounding. And this section will be more mathematical. Recording measurements, significant digits, and rounding. So there are essentially two ways to round. We can round a number using decimal places or using significant digits or significant figures. The terms are pretty much synonymous. using decimal places or significant figures. Decimal places are easier. When we use decimal places to round, we just say, okay, round to the third decimal place. So you take your number, you go 1, 2, 3 decimal places, and you stop there. Possibly changing it based upon the number to the right, which we'll see in a second. Significant figures is a little tougher. So what is a significant figure? A significant figure is a value of your measurement that you know for a fact, or possibly one digit past that. So if I have, a measuring device like a ruler or something, that is not what I'm looking for. So if I have a measuring device like a ruler or something, and it's like this, and here is dot dot dot. So here is the 10-inch mark, and here is the 11-inch mark, and so on. And so I'll say here's 12 inches at the end. And I have a device that I'm measuring which stops here. So I know for a fact that it's going to be 10 point something. I know that for a fact. It's between 10 and 11. No doubt, based upon my measuring device, that the 10 is correct. And then I might say, well, it's approximately 60% through, so I'll say 10.6. I'll use that as my measurement. I'll use my exact 10 and then one digit past that for a pretty sensible guess of 0.6. All three of these numbers would then be significant because they are all either known or one sensible guess digit past there. So let's do example 1. Example 1 says as follows. It says, for each of the following, determine the number of significant figures. So 21.35. So rule number 1, if it's not 0, it's significant. So this one immediately has 4 significant figures. Any non-zero number is immediately significant. No questions asked. 1.25, same principle. We have 3 significant figures, 3 non-zero digits. 305. Well, here we have 2 non-zero digits, so we have at least 2 significant figures, and the only question we have to ask is, what about the 0? Well, if you have a 0 sandwiched between non-zero digits, whether it's immediately between or the few zeros in between makes no difference. Significant, automatically. Because if I know 3 for a fact, and I know 5 for a fact, or perhaps 5 I don't know, but that's the one digit of uncertainty, and then I know the 0 for a fact. And therefore, we have 3 significant figures. Any 0 sandwiched in between, significant. 1009, same idea. 1, 9, significant. Any zeros in between, automatically significant. We have 4 significant figures. So now a little more complicated, 0.00300. So this is the first tough one because, as you'll notice, we have the 3, so we know that's significant, but we don't have zeros sandwiched in between non-zero numbers. We have some zeros preceding, and we have zeros after the fact. So we already know rule number 1 and 2 is non-zero digits are automatically significant, and zeros sandwiched in between are automatically significant. Rule number 3, preceding zeros, the ones that are before any non-zero number, are automatically not significant. Again, no questions asked. Any zeros that precede non-zero numbers, whether you have a decimal or not, automatically not significant. So what do we have here? We have the 3, but now we have 2 zeros after the decimal point. Well, here's the rule. If you're after the decimal point, like we are here, then trailing zeros, zeros at the end are also significant, because if they weren't significant, I wouldn't write it. I wouldn't need to write it. Mathematically, if I wrote 0.003, mathematically it's the same number. So what do I gain by writing the zeros at the end? It's the fact that I know that those are zeros, or again, worst case scenario, that extra digit of uncertainty but sensible guessing. So because of that, trailing zeros are significant, and in this case, I have 3 significant figures. Next case, 0.002, same idea. Leading zeros are not significant, so we throw them away, and therefore this one has exactly 1 significant figure. Now, we will learn soon something called scientific notation, which is what we use to write numbers in a way that we have no ambiguity, and we don't have to question and ask, are those significant? Are those not significant? We have a very precise way of doing that, which we will get to, but we're not there yet. So right now we still have a little to learn. Let's do another example. This is example 2. Example 2 says as follows: round the following numbers to the required number of significant figures. So the first one is 0.1235, and it says it wants to round to 2 significant figures. Well, we have 4 significant figures here. So if we want to round to 2 significant figures, we're essentially going to have those 2 units. So we round to 0.12. This is 2 significant figure rounding. Now, you might think, oh, this is easy. Just throw away all the numbers past what you're looking for. Well, then we have the following. This was A, and here's B. It says 0.2965. And it also wants to round that to 2 significant figures. So we know it's going to be 2 significant figures. So it's the 10ths place and the 100ths place. But this one rounds to 0.30, not 0.29. And you might ask yourself, well, what's the difference between the 2 cases? And the answer is, it's all about what comes next. If you look at 3, that's on the lower end of the 0 to 9 spectrum, which means 0.12 is closer to this number than 0.13 is. I'm not going to round up, which is so far away from 3, 4, 5, 6, 7, 8, 9, 0. I got to go all the way to the top, whereas down it's a lot closer, 210. So you always round to the closer number. But in the second case, where it's 6, it's faster and closer rounding up to 2 significant figures, 7, 8, 9, 0, than it is going down 5, 4, 3, 2, 1, 0. So the rule of thumb is, if the number next to where you're stopping at is 5 or more, round up to the next number up. And if it's 4 or less, 4, 3, 2, 1, 0, you round down. So here's question C. It says 415.25, and it wants to round to 3 significant figures. Well, those are the 3 units. The number to the right is a 2, so I go down. So this just goes to 415. And D, it says 3050, and it wants to round to 2 significant digits. So 30. So what's closer, 30 or 31? Well, neither of them are really close to 3050. So what do? Well, the number to the right is a 5, so we go up to 31, but we don't just write 31, because 31 is nowhere near 3050. We have to put in zeros afterwards. 3100 is the closest 2 significant figure number to 3050. So with 2 significant figures, we round up to 3100. Remember, trailing zeros are not significant. if there's, let me rephrase it, I apologize. After a decimal place, a trailing zero like here, 0.30 is significant. But we haven't had an example yet where there was no decimal points. In general, trailing zeros when there's no decimal point are not significant as a general rule. There's a little vagueness and ambiguity that we'll talk about in a few minutes. But for now, the general rule is that any trailing zeros before a decimal point, or in situations where there's no decimal point, are not significant. So let's actually go ahead and let's do this one and actually write out our rules for significant figures. Non-zero numbers, numbers are significant. Number 2, sandwiched zeros. And by that, I mean sandwiched between non-zero numbers. We'll just say between non-zeros are significant. 3, leading zeros are not significant. Leading zeros are not significant. Number 4, trailing zeros after the decimal point. Are significant. And finally, number 5, trailing zeros with no decimal point, like the one we have above, may or may not be significant. Now, this may or may not be significant is problematic because we don't want to have any vagueness when it comes to significant figures. And this is what I mentioned earlier about the concept of scientific notation, which removes this ambiguity. But for now, we have these 5 general rules. Let's do, actually, so that is the end. Oh, and I guess one more thing we should throw in as a rule. When rounding, always check the number to the right of the rounding spot. Rounding spots, we'll put a semicolon here. 0 through 4, round down, and 5 through 9, round up. Okay, so now that takes us to exercise 1A. At this point, you should stop this video, or in a minute, you should stop this video and try to do all of these exercises on your own. And only after you do them all, should you then look at the answers and check your work. But definitely try to do these on your own. Question 1. It says round the following measurements to 3 significant figures. So 9.478 meters. Notice that we have units now for the first time. The units must be included in your answer. So we are rounding 9.478 meters to 3 significant figures. That means we're going to go to the hundredth spot. So 9.4, and do we keep it as a 7, or do we go up to an 8? So when we look at the number directly to the right, it's an 8, so we go up, so 9.48 meters. This is a 3 significant figure rounding. This was A. B, 5.322 grams. 3 significant figures, so we're going to round to 5.32 grams. 3 significant figures. Part C, 1.8055 centimeters, 3 significant figures. 1.8, and what do we round to? Well, it's a 5, so we go up to a 1.81 centimeters, 3 significant figures. D, 6.999 inches, 3 significant figures. So what do we round to? Well, we look at the number to the right, which is a 9, so it goes up. Well, what is the next number that uses 3 significant figures and ends in the hundredth spot above 6.99? That would be 7.00. Notice how those 2 zeros are significant because they are trailing zeros after a decimal place. E, 4,578 kilometers. So 3 significant figures, approximately 4, 5, 7 goes up to an 8, but we don't stop here. 458 is nowhere near 4,578. So we have to throw in a 0 as a placeholder. And we round to 4,580 kilometers, where this 0 here is not a significant figure. Sometimes it is, sometimes it's not. Here it's not. F, 13,178 kilograms. 3 significant figures, 131, but the number after it's a 7, so we go up to 132. Of course, 132 is nowhere near 13,178, so we have to throw in zeros, not significant, to be close to our answer. So we have 13,200 kilograms. Again, 3 significant figures. Question number 2. Round the numbers in question 1, parts A to D, to 2 decimal places. Well, A through D, 2 decimal places. If you look at A through D, they're already at 2 decimal places. So we're going to have the same 9.48 meters, the same 5.32 grams, the same 1.81 centimeters, and the same 7.00 inches. All of these are 2 decimal places. Question number 3. Determine the number of significant figures in the following measurements. So A, 0.102 meters. Well, 1 and 2 are significant automatically, 0 sandwiched in between, so we have 3 significant figures. B, 1.002 decimeters. 1 and 2 significant, 0 sandwiched in between, 4 significant figures. C, 105 kilograms, 1 and 5 significant, 0 sandwiched in between, 3 significant figures. D, 0.001020 kilometers. Leading zeros, not significant. 1 and 2, significant. 0 sandwiched in between, significant. Trailing 0 after a decimal place, significant. We have 4 significant figures. And finally, E, 1 million micrograms. And this is the hardest one, because if you'll notice, if we go back up here, trailing zeros with no decimal points may or may not be significant. And the answer is, for this one, that we just don't know, because we don't know how the 1 million was measured. Was it really 572,000 and we just rounded to the nearest million? Or was it really 1,000,000.2 and we round down, but we're really close to a million? We just don't know. So the best we can say is it's at least one significant figure. This one is certainly a significant figure, but these guys, these 6, may or may not be significant figures. So the answer to this question is 1, 2, 3, 4, 5, 6, or 7 significant figures. And again, bad. Okay, I don't want to have this kind of ambiguity in my measurements. I don't want to have this kind of ambiguity in my calculations. So we need a method of not having this issue. And I promise you that method is coming very, very soon. But for now, technically, it could be anything from 1 to 7 significant figures. And then finally, question 4. It says, find the value of the expression 12.35 plus 21.14 plus 1.075 over the square root of 3.5 minus 1, and give your answer to 3 significant figures. So I take out my calculator, which everyone should have. TI-84 plus CE. It's one of my 2 favorite calculators. I also use a Hewlett-Packard, but that's not one that we're going to be using for this class because it's just not one of the acceptable ones. And we do first numerator 12.35 plus 21.14 plus 1.075. So this gives me 334.565 over. Now I'm going to put it in approximate equal here because when I do the square root of 3.5 and then I subtract 1, I'm only going to write a few digits here, 871. However, for my calculations, I make sure to use every one of those digits because I want to be as accurate and precise as possible. So I do 34.565 divided by what on my calculator is 0.8708286934. And this gives me approximately 39.692 ... So that's the value of the expression, but it says give your answer to 3 significant figures. So 3 significant figures, 39.6. Oh, the 9 tells me to go up. So the closest number is 39.7. And there are no units here. So that is my answer, 39.7. So that takes us through exercise 1A. Still in section 1.2, we now have example number 3. And example number 3 says as follows. A circle. So even before I read anymore, I draw a circle. I might need it, I might not, but I want to have it there. A circle has a radius of 12.4 centimeters. So the radius of the circle is 12.4 centimeters. Little side note, radius is one of those vague definitions in mathematics because it means 2 things at the same time. It means the length of a line segment that connects the center to the circle itself. And at the same time, it is the line segment. It's both the physical segment and its length at the same time. You know, fun note, impress people at parties. But anyways, a circle has radius 12.4 centimeters. Of course, all 3 of those numbers are significant. And it says calculate A, the circumference of the circle, and then calculate B, the area of the circle, and write down your answers correct to 1 decimal place. So in your SL and HL formula book, we are given the formulas for the circumference, excuse me, and the area of a circle. The circumference is given in the formula book by its traditional formula 2 pi r, 2 pi times the radius. The formula book uses lowercase r, so I'll conform with that, going back and changing that to lowercase r. And the area is pi r squared. Now notice that I used an equal sign for both of those because those are exact formulas. But when I plug in 2 times pi times 12.4 into my calculator, it gives me 77.9115 ... centimeters. And it says it wants me to round this to, what was that, 1 decimal place. So this is going to be approximately 77.9 centimeters. Oops. Meanwhile, the area, pi r squared, so I do pi times 12.4 squared. This gives me 483.051. Actually, if you go back here, if I'm going to do dot, 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 then this is actually a 4, even though it rounds up. And this is actually a 2, even though it rounds up. So 483.0512 dot, dot, dot. Units are area, so square centimeters, which I'm going to approximate to 1 decimal place, and I get 483.1 square centimeters. Notice how the units for area are centimeters squared, and the units for circumference being a length are just centimeters. Also notice that while I have 3 significant figures in my radius, I have 3 significant figures in my circumference, but I have 4 significant figures in my area. Now, that's not normally the convention that is used, but if they ask for a specific number of decimal places or significant figures, then you ignore all conventions and just do what they ask for, because that's what they're asking for. So when they say, give it to me to 1 decimal place, give it to 1 decimal place. So now let's go ahead and do exercise 1B. Like before, I would like you to stop this video, and I would like you to attempt all of the exercise 1B questions yourself. And after you're done, then go ahead and check the answers. So question number 1, round each of the following numbers as stated. A, 8,888. We want to round it to 3 significant figures. 888, the number after it's an 8, we go up. 889. Of course, 889 is nowhere near 8,888. We have to throw in a non-significant 0. B, 3.749. 3 significant figures. 3.74, the 9 tells us to go up, so 3.75, nothing to worry about there. C, 27,318, and we want 1 significant figure. 1 significant figure. Well, that means we stop at the 2, but because of the 7, it goes up to a 3. And then we have to throw in enough zeros to make this number match, to be close. And that's going to be 4 zeros, 1 for each spot. So 30,000. D is 0.00637, and we want 2 significant figures. So 2 significant figures would be those 2, because the first 2 zeros are not significant, and even now they're not significant. And because of the 7, it goes up, so 0.0064. You can't just say 0.64. That's nowhere near 0.00637. So the zeros are very important, whether they're significant or not, for making sure that our number is close to what we're approximating. And then E, the square root of 62 to 1 decimal place. Now, 62 does not have a perfect square root like 64 does. The square root of 64 is 8. So the square root of 62 is a little less than 8. Is it 7.9 to 1 decimal place? Is it 7.8 to 1 decimal place? Well, in calculus, we can round. There's some nice calculus techniques that let us round the square root of 62 to pretty good precision. But we don't have calculus at our disposal yet. So what we have is something that might be even better, which is a calculator. And when I do square root of 62, I get approximately 7.874 ... So when I round to 1 decimal place, it becomes 7.9 because the trailing 7 tells me to move up. So that's it for number 1. Question number 2. Round the numbers in the table to the given accuracy. So there's 5 numbers. So let's do A. But before we do that, let's make our table here. There's the number. There's a round to the nearest 10. There's round to the nearest 100. And then there's round to the nearest 1,000. So none of these are after decimals. 10, 100, 1,000. Those are all before decimals. So A, 2,815. To the nearest 10, what number that is a multiple of 10 is as close as possible to 2,815? Well, there's actually 2 that answer that question, 2,810 and 2,820. Convention says when you're right in the middle, you go up. So 2,820. To the nearest 100, which 100 is closest? That would be 2,800. And which 1,000 is closest? That would be 3,000. Much closer than 2,000. B, 75,391. So to the nearest 10, that would be 75,390. To the nearest 100, 75,400. And to the nearest 1,000 would just be 75,000. Closer than 76,000. C, 316,479. To the nearest 10. Let's throw this in here. Kind of have a nice separation. Okay. So we have 316,480 is closer than 470. To the nearest 100, 316,500. And to the nearest 1,000 would be 316,000. Because 316,000 is closer to 316,479 than 317,000 is. D, 932. Well, 930 is the closest multiple of 10. 900 is the closest multiple of 100, and 1,000 is the closest multiple of 1,000. And finally, E, 8,253. 8,250 is the closest multiple of 10. 8,300, the closest multiple of 100. And finally, 8,000 is the closest multiple of 1,000. Question number 3. Round the following amounts to the given accuracy. A, 502.13 EUR, I'm guessing those are euros, to the nearest euro. Well, the nearest euro would be 502 euros. I don't put in 0.00 because that's not the nearest full unit of a euro. B, 1,002.50 USD. I assume that's United States dollars, to the nearest 1,000 USD. Well, that's approximately 1,000 USD. C, 12 BGN, I'm not even sure what that is, to the nearest 10. Well, the closest unit of 10, the closest multiple of 10 is 10 itself. 10, 20, 10's a lot closer. And then D, 1,351.368 JPY. I'm just showcasing my political in economic ignorance here. I have no idea what this is. To the nearest 100 JPY. Well, let's see, nearest 100. So we have 1200, 1300, 1400, 1400. 1400 is the closest to the nearest 100 JPY. Question number 4. A circle, draw a circle. A circle has radius 33 centimeters. Okay, R equals, clean this up. R equals 33 centimeters. Calculate the circumference. Well, circumference is given by the formula 2 pi r, which you will have in your formula book. 2 times pi times 33 gives me approximately 207.3451 ... in units of centimeters. And it says write down your answer correct to 3 significant figures. That would just be 207 centimeters. Question number 5. The area of the circle, draw a circle. The area of the circle is 20 square centimeters. So the area we're told is 20 square centimeters, correct to 2 significant figures. They're telling me that this one here is significant. Remember, without them telling me, that's a little vague. So that is significant. Calculate the radius of the circle, correct to 2 significant figures. Well, here we have to do a little algebra. We know area is pi r squared. My goal is to find the radius, so I have to get that by itself. If I divide both sides by pi, then I get area over pi equals r squared. And how do I get r from r squared? I take the square root. So I get r equals the square root of area over pi. Notice, or note, that normally when you square root both sides of an equality, you need to throw in a plus or minus. It's called the square root property. If x squared is equal to 4, then x is equal to plus or minus 2. In this case, I don't have to because the radius is a physical quantity which must be positive. So the negative might be a mathematical solution, but it is not a physical solution. So then I take the area, which is 20, divide by pi, take the square root, and my calculator gives me 2.5231 ... and radius is a length, so it's in units of centimeters. And it says calculate the radius of the circle correct to 2 significant figures, so that will be 2.5 centimeters. And finally, question number 6. Calculate the volume of a cube. It's a cube, so let's draw a cube. Even though you don't have to, I like knowing what I'm looking at. Like this, something like, I know what I did wrong. It should go a little lower, like this. Okay, there's my cube. And we're told that it's 4.82 centimeters on a side. And we want to calculate the volume. Well, your booklet will tell you the volume of a cube. The volume of a cube, or a cuboid in the book, is a length times width times height. But because it's a cube, the volume, which is normally length times width times height, in our case becomes side cubed. I don't normally like using the letter S as for side because S and 5 can be very, very similar. So if you're going to use the letter S, make sure it's obvious that it's not a 5. So if the volume is equal to side cubed, well, all we have to do now is take 4.82 and raise it to the 3rd power. And we get approximately 111.9801 ... And it's cubic units, centimeter, centimeter, centimeter. So it's cubic centimeters. And then the problem says, write down your answer correct to 2 significant figures. So that's the first 2. So it's going to be 1, 1, and not 11, because 11 is nowhere close to 111. I do need a non-significant 0 placeholder, and I get 110 cubic centimeters. So this takes us to the end of section 1.2. Next video will be on section 1.3, where we continue talking about measurements and a measure of how accurate your measurements are to true values in those cases where the true values are known. And it only gets more fun from here on out. So this takes us to the end of section 1.1 and 1.2. Make sure that you know how to do all of the exercises from 1A and 1B. And if there's any questions, feel free to, of course, rewatch the video. But this takes us to the end, so I hope it made sense, and I will see you all soon.